Hey everybody, woo! Welcome to the practice exam for exam 4. This is chapters 18 through 19. Okay, question 1, let's just get into it. We have a little bit to cover here. Question 1 says, calculate the change in entropy that occurs when 35 grams of water condenses from a gas to a liquid at the normal boiling point of water, and it gives us the ΔH of vaporization is this, and the molar mass of water is that. All right, so something to think about kind of in this problem is that we've got something going from a gas to a liquid. A student pointed this out to me because I have a tendency to just grab all the numbers and throw them down and figure it out. But when it's going from a gas to a liquid, remember, if we've got some gas and it's turning into a liquid, it's going to have to let heat out in order to do this. This has got to be an exothermic process. So our ΔH vaporization is actually, well, it's not, it doesn't change that, but our ΔH here is going to be negative 40.7. All right, so something to consider. So it's going again from a gas to a liquid. In order to do that, in order to condense, it has to let heat out. That's kilojoules per mole. All right, so when we go to do this, now we can kind of start looking at the numbers. We've got 35.0 grams. We know that there are 18.02 grams in a mole. We know that a mole has negative 40.7 kilojoules. And we can calculate how many total kilojoules this would take. And we'll talk about why we're going to do that. Hopefully this is kind of muscle memory, because this is our old process. 40.7 divided by 18.02. And you get an answer of negative 79.05 kilojoules. All right, so that gave us our ΔH for this reaction. Now we kind of got to go back and say, okay, what's it asking for? It's asking for our ΔS. And we need something that relates those two things. But the only equation that we have that really relates those two things in a particular system that's occurring is ΔG equals ΔH minus T ΔS. But we don't know ΔG, right? Or do we? We totally do, because it's saying that this is happening at the normal boiling point of water. What that means is in an equilibrium, is going back and forth between actually being a gas and a liquid. And so at the normal boiling point of water, or any equilibrium, this ΔG is going to equal 0. If 0 is equal to ΔH minus T ΔS, our actual equation is ΔH equals T ΔS. I just added T ΔS to both sides. All right, so now we have our ΔH. Anytime we work with entropy, it's generally helpful to kind of turn this into joules instead of kilojoules. So I'm going to say negative 7905. 0, there was an extra stick that you could keep the number in your calculator if you want to. Joules is equal to our temperature. So it didn't straight up give us our temperature, but we know it was the boiling point of water. So that tells us also that our temperature is 100 degrees Celsius or 373 Kelvin. Times ΔS. And now we're solving for ΔS. So I just divide each side by 373. And we'll find out that our ΔS is equal to, so I'm going to do, just to keep all the numbers in my calculator, so this is my answer in terms of joules. 0.51 as it turned out to be. And then I'm going to divide it by 373. And I get an answer of negative 212 joules per K. All right, so I want to ask if this answer also makes sense. We went from a gas to a liquid. So it went from this messy situation to a less messy situation. And so it should make sense that we lost entropy, and negative would be the answer. All right, number 2, the combustion of this has an enthalpy, standard enthalpy of this at 273. Okay, so Let's go ahead, figure this out. This shouldn't actually say 273, this should say 298. I'm gonna go change that. Okay, so hopefully by the time you get this, your paper says 298, and that makes some more sense to you because we're talking about the standard enthalpy of the reaction. All right, so our reaction for C4H10 is 2C4H10, I'm doing this, let's see, from memory, plus 13O2 in equilibrium with 5H2O, that won't work. Plus CO2, how much CO2? We've had 4, which would have been 8. And our hydrogen should have been 10. I got it. So 2C4H10 plus 13O2, yielding 10H2O and 8 CO2 is what you should have. All right, the importance of that comes in a little bit later, but let's go ahead and focus on this first question right here. It says, what is delta S of the surroundings? And if you're concerned about how to balance this reaction, generally I would ask, but I talked to a lot of students and they said that this wasn't really covered very well in Gen Chem, so I'm not going to require you to know how to balance this reaction. Just assume that this reaction was already given to you. So this is 2C4H10 plus 13O2, yielding 10H2O and 8 CO2. Okay, so it says, what is delta S of the surroundings? Okay, this can be determined, use delta H to determine. How is that? Well, remember delta H is the amount of heat something has, so this is a combustion. So this is like something lighting on fire. It's letting out a lot of energy, and this is the energy it's letting out. This 2,888 kilojoules. All right, so if the reaction itself, if the system itself, like a barbecue pit or whatever you're using butane for, this is butane by the way, is lit on fire, the surroundings absorb that heat, right? So the surroundings are taking in that 2888. And that's where we came up with that delta S surroundings equals negative delta H over T. The negative delta H is because it accounts for what the surroundings are encountering, not the system. All right, so that would be a negative 2,880. 8.0 kilojoules, all divided by the temperature, which I said was 298 Kelvin. All right, let's go ahead and calculate this. I get an answer of 9.69 kilojoules per K. Oftentimes you'll get a decimal point here, and again, that's because generally when you're working with entropy, you'll want to turn it to joules. This was just such a large amount of heat, it didn't matter, you got a single digit, that worked great. You could have also gotten that 9,690, I can do it, joules per Kelvin. Cool. All right, so either of these answers would have worked. Great. All right, what is the sign of the entropy for the system? All right, so now we're talking about the reaction itself that is occurring. What's that system looking like? If you could cap a barbecue, for example, what would be happening inside that barbecue if you're burning propane? Well, you'd see that there's here 2 moles of butane and 13 moles of O2, and they're creating 10 moles of H2O and 8 moles of CO2, and all of these things are gaseous because water, when this stuff lets out this much heat, it actually becomes gaseous. All right, so what's the sign of entropy of the system? Well, on the left-hand side, we have 15 mole of gas, and on the right-hand side, we have 18 mole of gas. In other words, it's going from 15 to making even more gas inside there, adding even more chaos, right? So you have 15 things creating a mess, and now over here you have 18 things creating a mess. That means it gained entropy. It has to be positive. Up next, it asks for the sign of the entropy for the universe. All right, so we know that delta S of the universe is equal to the delta S of the system, so where this reaction is occurring, plus the delta S of the surroundings. What is that reaction doing to the surroundings around it? We know that the system was positive. We know that the delta S of the surroundings was positive. If you take a positive and add to it another positive, no matter what, you're going to get a positive. All right, here we're kind of in a similar situation in terms of positive and negative. I would have loved to put delta on those. You can. All right, so we're gonna talk about what's spontaneous or non-spontaneous, and this is kind of the table that you guys had already from your lecture. But I'm just gonna assign some arbitrary combinations here. So plus plus, minus minus, minus plus, minus plus. All right, so in order to, like we said, anytime we're relating enthalpy and entropy, we should be looking at delta G equals delta H minus T delta S. And another important consideration is that when delta G is less than 0, in other words, it's negative, it's going to be spontaneous. If delta G is greater than 0, in other words, when it's positive, it's going to be non-spontaneous. All right, so essentially we're plugging in these values, if it's positive or negative, etc., and seeing what effect that would have on delta G. Okay, let's start with this one. So the very first one, we have enthalpy that is positive and an entropy that is negative. Okay. If we have something that's positive and we subtract something that's negative, because don't forget, temperature is always going to be positive, by the way, because it's on a scale of Kelvin, so 0 and above. So if this is always positive and you subtract something that's negative, remember, if you have like 5 and you subtract like a -2, that's the same thing as adding that -2. So you get 7, you get a bigger number. Anytime you have something positive and you subtract something that's negative, you're going to get a bigger positive number, no matter what. And that's why if you're going to get something big or positive, we're talking about this delta G right there, which tells us this has to be non-spontaneous at any temperature. It doesn't matter if you're subtracting a big negative number or a small negative number, no matter what, you're going to get an answer that's going to be positive. All right, let's look at this next one. If you have positive and positive, okay, if you have something that's positive and you subtract like a little positive from it, so let's say that T is small, it says at low temperature, so if this T is small, so tiny positive, an example of that would be like 5 minus 0.2. Your answer is going to be positive still, right? You still get 4.8. So at low temperatures, you're still going to get a positive number. In other words, it will still be non-spawn. But what happens if you make that temperature bigger and this T delta S gets larger? Well, if this T delta S gets larger, this becomes a big positive. And you take a positive and you subtract a big positive, in other words, like 5 minus 18, you get -13. You get a negative number as a result. And if you get a negative number, that's telling you it's spontaneous, which is kind of cool because if you have something that's got a positive delta H and a positive delta S, you know if you add more heat, you can make that reaction actually occur without any additional outside resources. All right, now we got the negative and the negative. So if we have a negative and a negative, if we have a negative when we subtract a small negative, in other words, the temperature's down, so we're talking about right here, this low temperature, and you subtract something small, so like a -5 minus a -0.2, that's the same thing as adding, and you'd get a -4.8. So you still get a negative number. So if you have a negative and you subtract a small negative, you get a negative number. In other words, this one would be spontaneous. But if you have a negative and you subtract a big negative, for example, -5 minus a -20, that's the same thing as adding a positive, and you get a positive 15. In other words, the result would be positive. So as you add heat to something that has these conditions, the negative and the negative, you're going to make it more non-spontaneous. Last but not least, if we have a negative and a positive, so you have a negative number and you're subtracting a positive number, so like -4 minus whatever you want that number to be, 8, you'll get a negative 12. So it doesn't matter what this number is, how big or how small it is. You subtract a 1, you could subtract a million. No matter what, it's getting more and more negative. And that's why no matter what the temperature does to making this part bigger or smaller, this is going to be spontaneous every single time because it'll be less than 0. All right, moving on. Number 4. I have consider this reaction. It asks me kind of two things. A, calculate delta G, and B, if it's spontaneous, or if it's not spontaneous, determine at which temperature it will become spontaneous. So let's focus on A real quick. I'm going to do it up here. All right, I see delta H, I see delta S. That's what I'm going to use. Delta G equals delta H minus T delta S. You might be wrong, you know, who knows, but at least you got it out there and you can figure it out from there. But as far as I can tell, it wants me to calculate delta G. I've got delta H, I've got delta S. I even have the temperature there at 25 degrees Celsius or 273 Kelvin, so I'm good to go. The only thing is, this is in kilojoules. Should have been a lowercase k, by the way. And this is in joules per K. And so when you put them together, you want to make sure that, that you're not mixing them. You can't have kilojoules adding to joules. You have to make sure that they're both the same. So how I like to do that is just to move the decimal place of the kilojoules over to put it into joules, because I like working with bigger numbers rather than smaller. And then we're just going to subtract our T times our delta S. That allows our K to cancel, and we've got joules minus joules, which we're cool with. And let's calculate it. So 95,700 in parentheses 298 times, and I get an answer of 53,324 joules. And then you can always put it back in kilojoules if you want. 53.3 kilojoules, because this had 3 sig figs right there. That had 4, that had 3. So our answer is 3. All right. So that was great, but it says if the reaction is not spontaneous, what temperature did the reaction become spontaneous? So, all right, so our delta G equals this. Is that spontaneous or is it not? So this is positive number. So if it's positive, it's not spontaneous or non-spawn. So now we can move on to part B. So if it's non-spawn, determine at which temperature it becomes spontaneous. So we can go back to this equation right here. We know that a delta G greater than 0 is non-spawn, right? And we know that a delta G less than 0 is spontaneous. And so essentially the point where it goes from being a negative to a positive, or positive to a negative more specifically, is the point at which it becomes spontaneous. So if we set this equal to 0, we find that point directly. So we say 0 equals delta H minus T delta S, and like we did before, that's saying T times delta S equals delta H. We don't know the temperature we're solving for it. We do know the entropy is 142.2 joule per K. And we do know the delta H is 95,700 joules. So I'm going to take 95,700, divide by 142.2, and I get a temperature of 673 Kelvin, or just because of the mass EC on that one, or 400 degrees Celsius. Okay, moving on. So this would be the temperature. Anything greater than that, it would become spontaneous. All right, so we have this reaction, and it gives us this information. It asks us to calculate delta G. I got delta H, I got delta S, but these are formation enthalpies and entropies. So kind of like in Gen Chem 1, where you add up all the products, you take the sum of the products, and you subtract the sum of the reactants. That's what we're going to do in this situation for each one. And then we'll have our delta H, we'll have our delta S. We know our temperature, and we can solve for delta G. So that's what we're going to do. All right, so first it says calculate delta G. We couldn't do that if we didn't have all this information, or I could have given you tabulated delta G information of each formation. So let's go ahead and do it. Our products are over here. Our reactants are over here. So our delta H overall for the whole reaction is going to equal the number of moles of each one times the enthalpy for each one. And again, I'm adding up all the products and then all the reactants. So the products first, I got NH4 and NO3. So my delta H for the NH4 is negative 132.51. And that should be in kilojoules per mole. And this one, by the way, should be joules over mole times Kelvin. Okay, so I've got negative 132.51 kilojoules. Now I'm not doing it right now, but there's only 1 mole, so I would have multiplied this by 1. If this had been like a 4 moles here, 4 as a coefficient, I would have multiplied this by 4, right? So there's my products, negative 132 plus this NO3, a negative 205.0, to which I'm going to subtract everything added on this side. There's only one thing that worked out well, but that's going to be a negative 365.56. Also kilojoules. It was kilojoules per mole, but each of these again had just 1 mole, so I crossed them out. All right. So add your products, subtract your reactants. So we have negative 132, 32.51. Oh. Adding to that, negative 205.0, which doesn't matter. And then you subtract a negative 36, which is the same thing as adding a negative, or 365, so plus 365.56. And you get an answer of 28.05 kilojoules, which would be 28050 joules, just moving that decimal place 3 times. All right, now we can move on to delta S. Same thing, products minus reactants. So we're looking at this table. We have 146.4 joules per K plus 113.4 joules per K minus our reactants over here, which is 151.08 joules per K. Okay, 146.4 plus 113.4 minus 151.08. And I get an answer of 108.72 joules per Kelvin. All right, so we have our delta H, we have our delta S. Now we can kind of throw them together into our delta G formula. Our delta H again is 28050 joules minus 298 Kelvin times 108.72. 0.72 joules per K. So 28050 minus 298 times 108.72. And I get an answer of negative 4348.56 joules, or 4.35. Kilojoules. Actually, technically, I think this should have had somewhere. Nope, I'm good with that. I was looking at sig figs, but that's good. All right, rad. Now it says calculate K at the same temperature. So we've calculated our delta G, not just any delta G, our standard delta G, because we use standard enthalpies for each of these. And so when it says calculate K at the same temperature, that's when we can use the thing that relates K and delta G. So finally we're on to another equation, and that's this: delta G under standard conditions, or standard free energy, equals negative root link, RT ln K. Be sure you're paying attention to these ln's and logs. They're easy to get mixed up, and we do some of all of them. So make sure when you're looking at your equation sheet that you're using ln when it says ln. All right, so it says calculate K at the same temperature. Well, now we know our free energy, and I'm actually going to include this whole amount there. We know it's negative 4348.56 joules is equal to negative, our R would be 8.314 joules over mole times Kelvin. This again is R. We have to use this R because it has the joules in it, times the temperature, which again is 298 K, times the ln of K. Okay, so I'm going to get ln of K alone here. See if I can move it up here and save some room. So I have this number right here. I'm just going to divide by negative 8.314, divide by 298, and get an answer of 1.7552. So essentially I've got 1.7552 is equal to the ln of K. To get rid of K, you take E to both sides. So E to that power, this will cancel that out, and now we have E to the 1.75 whatever will give us K. So I do second E to the second answer. I get an answer of 5.78. If you get a slightly different number, that's okay as long as it's really, really close. That's just because I may have rounded somewhere in here, or you may have rounded yourself. So as long as we're getting something similar, hopefully we're doing okay. Something to think about right now. We knew our free energy over here was negative, so we knew that it was spontaneous, right? And remember that K greater than 1 is also spontaneous. So that's a good check. If you have those two things and they're opposite, something went wrong. Right, number 6, one of my faves. The whole reason I brought some extra paper. Okay, let's do this. All right, so we're going to balance these reactions under two conditions, acidic and then basic. So we will start by looking at the half reactions themselves and writing them down, and then we'll do one under acidic and one under basic. All right, so in this case, we had iron going from that to that, and if you remember, if the charge goes up, it was oxidized. It was oxidized. And eventually we'll talk about that being at the anode, but not in this problem. And then if we go from, that means this other thing had to have been reduced. And if that bugs you, you can calculate the oxidation number of manganese here. You'll find it to be +7, and manganese over here is +2. So you'll see that it went down. All right, given that information, let's break these things into their half reactions. So step 1, break them into half reactions. I'm not gonna go through this super slowly because there's another video that does it. And that one goes through a little more slowly if you want to. All right, so over here I've got a 2+, over here I got a 3+, so I know I need to add a negative over here. Now I have 2+ and 2+ total over here. Now I move on to my permanganate over here. And I'm turning that into Mn2+. Okay. Now kind of our instinct is to immediately add electrons, but this thing has oxygen over here and no oxygen over there. Remember, we have to balance elements. So to balance an element, it depends which conditions we're using them in. Again, this is the acidic conditions. So in order for acidic conditions, we're gonna first add water to balance oxygen. So we're gonna add 4 waters to this side because there are 4 oxygens over there and each water has an oxygen. Step 2, add H+ to balance the hydrogen. So we just added 8 hydrogens here. So that means over here, we want to add 8 hydrogens. Step 3, balance a half reaction with electrons. Okay, so we already did that with this one kind of right away. But over here we need to balance with electrons. So my charge over here is a total of 8 positives and 1 negative. In other words, a total of 7. Over here, my overall charge is 2 + 0, which is 2. So I have to add electrons to one of these sides to get them to equal out, and I can only add negative charge. So always add it to the more positive thing to bring the negative charge, or to bring the charge down. So I need to add 5 electrons over here, because if I add plus -5, I'd get a +2. All right, so last but not least, we gotta make sure each half reaction, electrons can cancel. They can only cancel if they're the same number. So up here I have 1 electron, down here I have 5 electrons, that's not gonna work. So I can only multiply, I can multiply both by something or 1 by something, whatever. The easiest thing I see is to multiply all of these by 5, and that will give me 5 electrons here eventually. So when I do that, what I get is 5 Fe3+, yielding 5, Fe2+, and 5 Fe3+, plus 5 electrons. And now I can add those suckers up. So don't forget, we're talking about all of this stuff except for the 5 electrons, which will cancel. So I've got 8H+, plus permanganate, plus 5 of these iron 3 ions, yielding Mn2+, plus 4H2O, plus 5 of these, did I do this again? Iron 2, plus 5 of these iron 3 ions. It's because it still look like a 3. That's a 2, everybody. I'm just gonna rewrite it. This, by the way, is also a 2 because it was on the left-hand side of the arrow. All right, so now we have all these things added up. This is technically our balanced reaction, but we want to make sure that everything works. So final check would be make sure that you have the same number of electrons on each side. So over here, or same number of charge on each side, I should say. So over here I have 8 positive from these 8 hydrogens, plus 1 minus from that, plus 10 positive from the 5 Fe2 pluses, for a total of 17. Over on this side, I've got 2 positive from the manganese, plus 0, plus 5 times 3 is 15 positive. also for a total of 17. So we're good, it's looking balanced. Hopefully we feel good about that one. That's the acidic conditions. So step 5, by the way, was add up. All right, so we did acidic conditions, let's do basic conditions. Very, very, very similar process, but with a couple caveats. Additions, really. Okay, so our first half reaction is the same. We got Fe2 plus, yielding Fe3 plus an electron. So same exact situation, we're breaking into half reactions. I've got my other half reaction, MnO4, yielding Mn2 plus. All right, so once we break it into half reaction, same situation. We're gonna add H2O to balance oxygen. So over here, I need to add 4 waters. Step number 2, add H plus to balance the H from the water. I added 8 new hydrogen, so I have to add 8 H pluses. Step number 3. Step number 3 is where things get different. You want to add OH minus for every H plus. So over here I added HO on both sides. So over here I added 8 H pluses, so I want to add 8 OH minuses to both sides. Step number 4, H plus OH minus equals water. For every H plus you have and every OH minus you have, you change them into water. So here I have 8 H pluses and 8 OH minuses. In other words, I have 8 waters plus MnO4, yielding Mn2 plus 4 H2O plus 8 OH minus. All right, cool. So we're doing pretty well. I probably should have listed that this is basic, by the way, in case you didn't get that. We're on part B. Okay, and last but not least, or maybe next, now we can balance the half reactions. Reactions with electrons. At this point in time, you can cancel waters if you want to. You can wait till the end or whatever's comfortable, but I mean, at this point, it's kind of just heavy extra baggage that we're kind of carrying around while we're doing this, so I'm going to cancel them. By canceling them, I mean over here we have 4 waters, and over here we have 8, right? And anything on both sides of the reaction is going to cancel. So I can cancel all 4 of these with 4 of these over here, meaning this is no longer there, and I only have 4 of these waters left, if that makes sense. So let me rewrite the whole thing just to make sure it's clear. All right, so now we're going to add electrons. So over here, I have a total charge of -1. Just kidding, plus my 8H plus, which, nope, just kidding, we're good. Total charge of -1. And over here, I have a total charge of 2 plus -8 for a total of -6. So -6 over here and a -1 over here. I need to add, again, always adding electrons to the more positive thing. I need to add 5 negatives over here. In other words, 5 electrons over there. So now I have a -6 over here and a -6 over there. All right. So now we've got our balanced half reaction. Now we need to make our half reactions cancel, so the electrons can cancel. What I mean by that is sometimes you have to multiply one or the other, etc. But thankfully this has 5 electrons, so we really only need to multiply this one by 5 to get them to have the same number of electrons. If we'd had a 3 and a 2, we would have multiplied this by 2 and that by 3, etc. So I'm multiplying this whole thing by 5. And now I can add them up. I have 5 Fe2 plus 4 waters plus permanganate, yielding Mn2 plus 5 Fe3 plus 8 OH minuses. And the reason I didn't include the electrons is again because they would have canceled like that. Last but not least, let's look at these charges. Okay. So over here, from my 5 Fe2 pluses, I have a positive 10 plus a negative 1, or a total of negative 9. And over here, I have a positive 2 plus positive 15, 5 Fe3 pluses, plus negative 8, which also happens to be negative 9. So we have the same charges on both sides. That's a good sign, and hopefully feeling okay. This would be our balanced reaction right there in basic conditions. Woohoo! We're moving. Last page. Number 7 says find K for the following redox reaction at 25 degrees Celsius. All right, so let me think of this. So there are a few steps we're going to use here. Remember, when we're solving for K, we're probably, we need to look at something. Do we have concentrations? Do we have pressures? If so, we can use those to solve for K. Do we have delta G? We can use that to solve for K. But we introduce something else, which is when we have the potential of this stuff. And in those cases, we can solve for K. So the equation for that, anytime we have redox reactions and we're solving for K, is that the standard cell potential is equal to 0.0592, which is again just R, T, and Faraday's constant combined, divided by N, times the log of K. Pay attention to the way I say log is because I want you to pay attention to the fact that it's a log, not a natural log. It's a log base 10. Okay, so let's go ahead and figure this sucker out. When I did a bad job because I don't have a cell potential table. Dang it. Okay. Well, if you were to look at your potential table, you would see the following. You would see Zn2 plus 2 electrons yielding zinc. And it would tell you that the E for that cell is negative 0.76 volts. And the potential for that half reaction. And then you'd have another one, and it would say 2H plus 2 electrons yielding H2, and it would tell you that that potential is 0.00 volts, or just 0, as we discussed today. All right, so this is what your book would tell you when you look at the potential table. And the reason we're looking at that is because we have zinc going to zinc 2 plus, and hydrogen plus going to H2. So these are the things that we're looking for in the table. All right, another thing to recognize is the order in which these are written. So here we have zinc going to zinc 2 plus. Hopefully you agree that that was oxidized. And we know that that happens at the anode. Oxidation happens at the anode. These valves stick together, AO. All right. And up here, we had a positive, it went down to a 0. In other words, it was reduced. And that happens at the cathode. So we know our cathode, and we know our anode, and we know the numbers here for our potentials. I also know that if I flip this thing around and went to add these half reactions up, that these 2 electrons would cancel because they're the same number of electrons. So that also has me thinking about my N. Before we get there though, we need to calculate this E cell. Again, that equals E cathode minus E anode Our E cathode is, again, the hydrogen right here, 0.00 volts, from which I'm subtracting the anode, which is negative 0.76 volts. You add them up because it's subtracting a negative, and I get positive 0.76 volts. So that's my E cell. So that number I'm going to plug in up here. Again, my N is 2, and that's just because these half reactions, I don't have to multiply them by anything to get their electrons to be different numbers, or to get electrons to be the same numbers. They already happen to be the same number. Okay, so 0.76 volts is equal to 0.0592 over 2 times the log of K. And again, we're solving for K. So let's do it. 0.76 times 2 divided by 0.0592. I multiply that by 2 divided by 0.0592. And I get that 25.68 equals my log of K. To get rid of log, specifically log base 10, you have to take 10 to both sides. So 10 to that side tells me my K is equal to 4.74 times 10 to the 25. And yep, that's pretty cool. So hopefully it makes sense. That's another question that we want to ask ourselves. Remember, we had a positive E cell. We know that that means it's spontaneous. We had a K that's greater than 1. That means it's spontaneous. So those little checks you can do to make sure that everything's on track end up being kind of important. So it is on track and we're looking good. The delta G for this, by the way, would be negative. And that's kind of where we're coming in the next one. Oh, just kidding. I didn't ask you for delta G. That's cool. So this next one, though, is kind of fun. I might pull in some more paper. Okay. So this sucker's awesome. So the reduction potentials are given to you. And the half reactions are given to you. And it wants you to find Q and Ecell. This is kind of a hint, by the way, that it gave you Q. It might have just asked for Ecell, and you'd recognize that that's not Ecell with the little circle, telling you that this is a very specific conditions that aren't at equilibrium, and we want to calculate the E that they have right then and there. So the reaction or the equation we're going to be using is that Ecell equals the standard Ecell minus 0.0592 volts over N times the log of Q. Because again, this isn't at equilibrium. We're looking for a specific set of information. All right, it tells us various things, but first it asks us to find Q. Remember, Q is products minus reactants, or products over reactants, right? But we can't do products over reactants if we don't know the reaction in general anyways. And so we have to make this assumption that we're going to control the reaction. Remember, the most negative thing in a spontaneous reaction is going to be the anode. Again, that's because it's the most negative. That makes this guy the cathode, because it's a bigger number. All right, with that being said, remember, oxidation happens at the anode. Right now, we're going from a 2 plus to a 0. That's not oxidation. The reason these say reduction is because they're the reduction potentials. This is currently a reduction reaction. We don't want it to be. We want it to be the anode. So we're going to flip that sucker around. That doesn't change the E, the E that we're looking at. So the E for Cn still stays the same at negative 0.76 volts. our silver was already the cathode. We know that that's where it was reduced. And that's what's happening. It's going from a positive to a 0. It's reduced. ReG equals positive 0.80 volts. All right, but if I were to add these up and get our overall reaction, which is our goal in order to find Q, we must find reaction. We can't do that because this has 1 electron and these have 2. So we have to multiply this whole thing by 2, right? So I'll have to put a 2 there, a 2 there, and a 2 there in order for these to cancel. Now my 2 electrons can cancel with my 2 electrons and I can add them up. Now we have 2 silvers plus a zinc, 2 silver ions plus a zinc, yielding the zinc ion plus 2 silvers. All right, so this is our reaction. Now we can go back and look at the concentrations that it talks about. It said that, and we're not worried about the solids. These things that are neutral charges, these are the solids. These things with ionics, these ions over here, they are the ones that are going to be aqueous. All right, so here we have zinc, and it tells us that it's 0.10 molar. And tells us that our silver ion is 0.150 molar. Right? And so when we go to find Q, Q is going to equal our products over our reactants. Solids are excluded from that. So we just have 0.100, which would be our zinc, divided by our reactants, 0.150, but because there's a 2 there, this is going to be squared. All right, so our Q, I don't know why I added 0, and we get 4.44. And that's our answer for A. It asked us to find the Q, and that's our Q. The next part said find Ecell. Again, that's where we're going to be using this reaction, or this equation, excuse me, right here. We first need to find the standard cell, because we know N, it's going to be 2 here, and we know Q, but we still need to find the standard cell. Ecell here is the cathode minus the anode. We know that the cathode was 0.80 volts minus our anode, negative 0.76 volts. In other words, subtract a negative is the same as adding a positive, we get 1.56 volts. That's our Ecell. So under standard conditions, this battery is giving us 1.56 volts. Now, when we go to plug this in to our equation here, we say 1.56 volts equals negative 0.0592. Divide by our N, which again was 2, because that's the number of electrons you canceled on both sides, plus the log of 4.44 repeating. Oops, minus, sorry. And that whole thing is going to equal our Ecell. I don't know why I put negative. I can do it. Minus. Just plugging and chugging in this equation. All right, let's go ahead and calculate this out. I have 1.56 minus 0.0592 divided by 2 times the log, our last answer. I get an answer of 1.54 volts. So under these conditions, my battery that I had made out of this reaction went down just a little bit in terms of its spontaneity. It got more positive. Let me rephrase that. The delta G got more positive. The Ecell got more negative. In other words, you can see it went down. Remember, big positive Ecell tells you that it's spontaneous. This is smaller, so it's less spontaneous. This would be our answer. I'm just pointing out that this is a little less spontaneous because that'd be a easy, quick question I might ask. All right, y'all. I hope this helps. gives you something to study, and yeah, hope you have a good day. Bye.